Hello, we are the Machine Learning in Real Estate team, and this is our demo for Sprint 5. These are the things that we'll go over in this demo. First, we'll talk about a recap on root protection, then data collection, then deployment, then updates on our model, and finally, the sprint review. So first, we'll talk about a recap on root protection. So for the sprint, we planned on implementing some sort of root protection. But after talking with our mentor, we learned that this was no longer necessary because the build-up infrastructure uses Nginx for load balancing and routing requests. And our model is deployed internally within the build-up infrastructure. So requests to the model can easily be filtered by IP address using the currently existing request routing methods that are being used by build-up now.
Now onto data collection. Just to recap, last sprint we were still working on getting and cleaning all of the data. So far and currently, we are done with all the data collection and cleanup of San Francisco, Boston, and Austin cities with 4 million data points that we've labeled and extracted permit descriptions from. We have mapped the data into 4 general permit types: electrical, building, mechanical, and plumbing. And for training, we've divided the data 80-20 for training and testing our model. After speaking with our mentor this past week, we will be creating an additional mapping to retrain the model and create a binary classification. We will be grouping the building, electrical, and plumbing types into a pre-construction label and the mechanical permit type into a post-construction label. Ultimately, this is because our mentor has pointed out that the most useful data for the build-up platform users is to have primary knowledge of what stage a construction project is in. And having these classifications will give the user a clear picture of such.
So the deployment. In our previous sprint, we talked about to set up a simple script to deploy our model in the API to the server or any other device, like any other server we want. So the procedure of our script is the following. First, we will get the model from the Google Drive because our model is super large now and we have a lot of data points. So it will be like much more than the GitHub can host. And then after we get a model, we'll create a folder to store it. And then we get a code, the API code, the Docker file, the requirement text, like something like that from the GitHub. And then we will just clean it up, like move the folder around to a certain structure so that we can run our API, the Python Flask API correctly. Then we build the image and run the container, like using the script. Like we build the image, we start the image, and we use the image to start the container. Then inside the container, we use the Docker execute to send a command to the container to run the API. In this case, we will have working API on the server or on the other, like on the server, and you will save a lot of time for us, for example, if we make a small change, we need to redo everything together. It will take up like 5 to 10 minutes to complete it. But for now, we can just run the script, and the script will do everything for us. And here's a quick demo. Now, this is the test server folder for inside our server. So because we don't really wanna mess up with our current running API, so we create another folder to test the script and other step, but like it will work as the same like the other folder we are using. So for now, we will use the get sh, and once you run this, you will have we already installed everything, so we don't need to install the stuff we need. And now we are downloading the folder from Google Drive. And after that, we are cloning the GitHub repo, and you will download everything we need. And after that, we build a Docker image, like what we're seeing right now. We build an image and download everything from the requirement test, like the Flask, the Pandas, TensorFlow, that kind of stuff. And for now, we already have since we're already run it 1,000 times before we do the demo, so most of the requirement is satisfied, so we don't need to run it again. And now that it is installing the relevant relevant to we want and will be posted for a while because it will take. So after that, we are building the container and like build the image and run the container, and then you will deploy the run the API, start a Python Flash API inside the container. But here's why we fail, because we are currently running the API on the server. So you can be you can run the same API on the same port, so that we don't want to change that because we are gonna use the script use the script for the future, so we don't want to mess that up. So now we have a not running container, but it indicate that it actually tried to run the code, but it just failed for another reason. So that's how the script look like.
Model update. In this sprint, we were able to finally train our model to use data from more cities other than Boston. In particular, we collected data from San Francisco and Austin in addition to Boston. For the final model, we used 4.3 million data points for training, of which 3.4 or 80% was actually used for the training phase, and the final 20% was used for testing. We realized that the 20 split is probably too large for our testing set, but we didn't get a chance to go back and allocate more for the actual training. Some of our modified training parameters were the number of epochs. We reduced that from 3 to 2, and this was to save time. In the final training, the model took a very long time to train. For 2 epochs. It took around 20 hours using our GPU. We also increased the batch size from 32 to 64, and this is to maximize GPU uses. We tried going past that, but our GPU didn't have enough memory. So for this version, we initially achieved 71.5% on the validation and 78.5% on the training set. And by looking at this, we suspected there was a problem because of the accuracy difference between the test and validation sets. Usually those two should be the same, or the accuracy on the testing set should be lower. But in this case, it seems a bit strange. So we went back and we suspected that the problem was that when we aggregated the data from the 3 cities, we didn't shuffle them. So when we divided the data into testing and training, we took the first 80% of data points as the training and the last 20 as the testing. So in that case, there was a high chance that the testing set consisted of data from only 1 city. So we, after realizing our mistake, we retrained the model and we shuffled the data randomly into the 80-20 split. And our final model was able to achieve a 74.84% accuracy. And this is consistent between the validation and the testing sets. So in comparison to the consulted paper that we looked at to do this job, in terms of the cities used for training, they used Austin, Philadelphia, San Diego, and New York City. For our model, we decided to use Austin, San Francisco, and Boston because these cities are more relevant to build up than some of the city, like maybe San Diego, which is not as popular. For total training data points, the paper used 2.2 million and our model used 2.4. In terms of model input preprocessing, the paper used a lot of preprocessing methods, including only training with the permit description, as well as using a word embedding mechanism outlined by Chloe. And then they also truncated the input to have less than 50 tokens. We didn't do the last 2. We used the naturally written permit description like they did, but for the rest of the preprocessing steps, we left it up to the small BERT preprocessor that was outlined by the BERT model to do our preprocessing. Both of the 2 models use BERT as the core architecture. In the paper's case, they used the real BERT model originally outlined by Google, and we used the small BERT model, and this was a design choice because we didn't have the necessary resources to train the bigger model. In terms of accuracy, we both have the same 4 categories: plumbing, electrical, mechanical, and building. And the paper say they achieve a 77.2% average on the 4 categories, and we achieve a 74.84%. We think this is on par with the results of the paper, considering that we use a small BERT model and we didn't pre-process the inputs as much. Also, we train our model on different cities, and the number of cities we have is less, so we don't have like too much of a heterogeneous data.
Here's our Sprint 5 review, and this is our burndown chart. Unfortunately, we forgot to update our issues until the very end, and so we have this steep drop on the chart. However, we were able to complete all of our tasks for the sprint. In the next coming days, and to finish up the project, we will be regrouping the data from the 4 categories to the 2 categories that we mentioned earlier into pre-construction work and post-construction work. And then we will retrain our model into a binary classification job. And our goal is to increase the accuracy to above 95%. And our mentor says that this will be the most useful to the build-up platform, so that's what we're aiming for with these last model retrainings that we're going to be doing. We're going to be documenting everything as well and leave everything packaged and nicely delivered to our mentor for build-up's use.